if V is a vector space of dimension n, then the use of coordinate vectors allows us to look at vectors in V as vectors in Rn. Okay? So the basis elements of V in that case take the role of the standard basis elements E1, E2, up to En. And this is what we saw, for instance, in this illustration. So the first vector with respect to basis B takes the role of this coordinate vector in R2, and this second guy takes the role of 0, 1, the vector 0, 1 in R2. And representing vectors in V in terms of coordinates enables us to apply to V techniques that we know for Rn, and this saves us some computations. For instance, suppose we have a vector space V which is not necessarily Rn with basis B. Okay? So if we want to find the subspace spanned by a set of vectors in V, then what we can do is we can compute the coordinate vectors of these guys with respect to basis B. Okay, so we will be able to represent them as column vectors, and the answer to the problem will be obtained by simply computing the column space of this matrix, so where the columns are the coordinate vectors with respect to of these vectors. To give another illustration for that remark, we call this procedure for constructing a basis from a spanning set in Rn. Okay, so this is only for Rn, but if we are going to construct a basis from a spanning set in a vector space that is not necessarily Rn, okay, so what we do is we consider coordinate vectors. Okay, so we fix a basis for the vector space and then compute the coordinate vectors with respect to our basis, the chosen basis for the vectors in question. Okay, and then we may proceed as in the procedure described for Rn, because after doing this first step, our vectors will then be represented by column vectors. So the same is true if we want to construct a basis from a linearly independent set. So recall the procedure for Rn. This is for Rn. If we want to answer this question for a general vector space, we can consider the coordinate vectors with respect to some chosen basis. Okay, so the first step is always to represent vectors as coordinate vectors with respect to a chosen basis, and then proceed as in Rn. We end this video by giving an application of the concepts of linear combinations and spanning sets on curve fitting. Suppose P, Q, and R are points in the Cartesian plane. So let's determine if P, Q, and R are linear, meaning lying on the same line. And if they are, let us find the equation of the line through them. So because the x-coordinates of the 3 points are distinct, a line that contains P, Q, and R must be of the form y equals mx plus b if it exists. So these 3 points must satisfy this equation. Okay, so 3 must be equal to m times 1 plus b, negative 5 equals m times negative 3 plus b, and 5 equals m times 2 plus b. Okay. In other words, we have to determine m and b such that this equation is true. So this is a linear system with two variables. So the matrix of coefficients is given by 1, negative 3, 2, 1, 1, 1. So this guy, this is the vector of constants. So to solve this, we apply Gauss-Jordan on the augmented matrix. You can check that after doing these elementary row operations, we'll arrive at this matrix in RREF. Okay. So from this, we see that the system has a unique solution given by m equals 2 and b equals 1. So the 3 points are collinear, and the equation is given by y equals 2x plus 1 for the line passing through the 3 given points. And the last problem, we solve for m and b satisfying this equation, and an alternative way of saying this is that express the vector 3, negative 5, 5 as a linear combination of these two vectors. Or so to answer the problem, a line through the 3 points exists if and only if 3, negative 5, 5 belongs to the span of these two vectors. In practice, we are usually given a set of data points. So, say n data points, and would like to determine the line or the best line describing the data. In that case, we must determine m and b satisfying this matrix equation. And as we saw earlier, this is equivalent to saying that this vector lies in the span of this vector and this vector. In general, the data points may not be collinear, so m and b may not exist. In that case, we settle for the vector or for this linear combination which is closest to the vector or the given vector y1, y2 down to yn. In that case, you may combine linear algebra techniques with optimization techniques. And the idea described here above can be applied to finding the best curve that fits a given finite set of data points. That's a good place to stop.